Welcome back, everybody. This is AP Chemistry, and we're looking at Unit 7, Section 1. And this entire section, or entire unit, is about equilibrium. Now, equilibrium, chemical equilibrium, is a state where the concentration, and remember this is the symbol that we use for concentration, of all the reactants and the products will remain constant with time. Now, this is a brand new concept for us in AP Chemistry, and chemistry in general. We typically don't talk about this much, in that everything we've been telling you is after everything is all settled down. So if I have the case where I have added in one nitrogen and three hydrogens, to this point we've been saying you just get two ammonias out of it. Okay, just two ammonias. But in reality, as we're making these ammonias, these will tend to break down and go backwards. In other words, the reaction will go both ways. And this double arrow tells us that the reaction is in a state of equilibrium. And so as I add more of these, they're going to go over this way. As I add more of these up and they get more concentrated, they're going to decompose back and so on. In fact, there's actually three types of reactions that form the equilibrium, or formed by equilibrium, I should be saying. Okay, so the forms that we see, this is one example of a synthesis. Okay, synthesis is where I take A plus B and I get C off of there, but it will, as I build up C, then it'll break down back into there. That leads into the next type, which is going to be what we refer to as a decomposition, where I get C will decompose into A and B. And then as I get more A and B, it'll actually synthesize back up into C again. And the third type would be this type that's referred to as a single replacement, where if I have something like an element or whatever of A, and I mix it with a compound of B and X, this will form, sometimes kick out the B and form an AX, and I'll get this. And as I get more of the B's, then all of a sudden it'll start to attract to this. And so the concept is that each of these types of reactions are actually reversible. There are some that do not form the equilibrium. Okay, and these are all, if you recognize these from Gen Chem, these are the types of reactions that we typically teach. Another type that would not form equilibrium would be the double replacement. Okay, so an example of that would be like an AX plus a BY. Well, they're going to just swap partners, and so we would get AY plus a BX. Those aren't going to form equilibrium. And the last type would be our combustion reactions. Combustion reaction is a special type that involves hydrocarbons. So I'll just give you an example of methane. And so we combine that with oxygen, and I get carbon dioxide and water as products there. This is not going to be a reaction that would be reversible then, and so we've got those. Okay, so the concept is pretty simple with this, in that as one thing builds, it's going to do some other things to it and reverse. And so the law of mass action will describe that equilibrium condition. And so here's your equation for it. If I have a large value of K, if I have a large value of K, what that means is the direction is going to go this way toward my products, okay? If it's a small value of K, the reaction is actually going to go backward toward the reactants, okay? As it builds up, it will do that. Now, you see that the equation is quite simple. It's just finding the value of K like we've always done. Notice that we still have our coefficients being accounted for, raising to the powers and so on. And it is worthy of noting at this point that this will only be referring to the aqueous states as we go. If we have something, for example, like a liquid, remember we use a lowercase l for that one, and also a solid. Well, those are not going to be factored into the K calculations. They just count as one for the concentrations. So they're a non-factor, if you will, as we take a look at those. So if we have some different examples of this that are coming up, we just take a look at our equation. It's not too bad as we look at this. Let's calculate the value of this equilibrium, the Kc, if you will, if N2 is this and so on. So remember that my value for my constant, my equilibrium constant, is going to be a concept of taking my, let's see, my product was going to be my ammonia. And so that was to the second power. I had my nitrogen, that was to my first power. And I have my hydrogen, that was to my third power. All right, so we just plug in values, don't we? This isn't too bad. We just take a look and we go 0.031, and that's going to be squared, over my 0.85. This one's a little bit more concentrated. That's to the first power. And then I have 0.0031, and that's to the third power. Okay, so if I look at this, I end up with 1 over 3.8 times 10 to the fourth. And so my Kc value is going to end up being 2.6 times 10. Oh, I'm sorry. That ends up being 3.8 times 10 to the fourth power. Okay, so that seems like a pretty, this is 38,000, and so that means that this reaction is going to be going this way toward the products quite readily. Okay, so very straightforward with that type of thing, and it would favor the products is how I would interpret that value. Now let's take a look at our Kc value if the reaction was going in the opposite direction. All right, and that's where the other number that I was screwing up came from. So I have my Kc value. This is going to be of my nitrogen now times my hydrogen. Again, we're just taking a look and seeing which direction would this reaction go. And so that was NH3, and that was to the second power. Okay, so if I plug in my values now, I end up with a 0.85 to the first times a 0.0031 to the third, and that's going to be over 0.031 squared. So my value ends up being 1 over that 3.8 times 10 to the fourth, which gives me a value of 2.6 times 10 to the negative 5. That's if it was going toward the reactant side. So obviously this is going to be something that's going to favor the products, okay? This is a reaction that's going to be going. All right. So let's take a look at some examples now that would see putting everything into action. And if we're given our K value, okay, so this is a different situation in that the first one I was looking for that. Notice that this is a very small number. I would expect that this is not going to be making much product. Okay, and I want to watch out for a couple of things here because there are a couple scenarios that we need to pay attention to. First of all, remember we're talking about concentrations. We have a 2-liter container, don't we? And so I have to do some side math here. My nitrogen, I have 0.5 moles over 2 liters. And so if I need to find my concentration, this is going to be a 0.25 molar. Okay? Now, if I take a look at my oxygen, I have 0.86 over my 2 moles. And so that ends up being a 0.43. Okay, so that's my concentration for my oxygen. Now, if I have my concentrations here, notice that we want to see the equilibrium concentrations for all of them. So we don't know this. That is an unknown, isn't it? Well, when we start this, we're putting them into a container. And so if I track this a little bit, this actually becomes a little bit of a stoichiometry problem. And if I track this, I'm going to show you a brand new technique. We started the initial values of something is going to be a 0.25. My initial value of oxygen is going to be a 0.43 molar. Okay, so that's what this I stands for, is initial. Now, when we just started this, notice that I didn't have any of the nitrogen monoxide being made. Now, the problem is we don't know this change as it's going back and forth, back and forth. There's going to get some product in there, but we don't know how much. And the question is asking when all is done at the end of equilibrium. Okay, so my change is going to be an unknown. I is for initial, C stands for my change. So if I create something called an ice chart, we can see what's going to be happening at each of these stages. Make yourself a box with this, and here's my ice chart, my initial values. Now, I'm going to be losing some of this product going over toward my reactant, I'm going to be losing some of my reactant over toward the product side. I just don't know how much I'm going to be losing. But notice that if there's a 1 here, there's also a 1 here. That means I'm going to be losing an exact same amount from the oxygen. Now, where's it all going? Well, it's all going to the product side, and I've got 2 of those. And so this guy is going to be gaining the exact same because of law of conservation of mass. Whatever this side loses, this side gains, and there's a value of 1 to 1 to 2, so I get a 2x here. So at the end of equilibrium itself, I end up with a value of 0.25 minus my x. On this side, I have 0.43 minus my x. And on this side, I end up gaining 2x. Okay, so let's use our constant value, or our equation of Kc equals the NO squared over my N2 to the first power times my O2 to the first power. Now remember, we know my Kc value. That's going to be 4.1 times 10 to the negative 4 equals 2x squared over my 0.25 minus x times 0.43 minus x. And both of these were to the first power. So notice we're just going to be doing algebra, aren't we? So if I keep on deriving this a little bit, I'm going to be multiplying these guys in here. This guy ends up being 4x squared on top. Okay, but down below, this ends up being 0.25 times 0.43. This ends up being 0.25 times negative x, and negative x times 0.43, and plus x squared. But here's something I want you to realize. My constant here is so ridiculously small that whatever I'm going to be losing here, really, if I'm just subtracting a very, very small amount, because remember, it's favoring the products, if it's only losing a very small amount to go to the products, we can ignore that value. If k is very, very small, I can ignore my x. In other words, I can cancel it out. And so this becomes 0.25 times 0.43. Obviously, you're going to be seeing later on in this unit what happens if I can't ignore it. But you can see we're going to distribute that out, and we're going to have to use our quadratic formula and all those things. Okay, so this ends up being 4x squared over 0.1075. So remember, those all equal 4.1. So let's get 4x squared by itself. I'm going to multiply 0.1075 times my 4.1 and times 10 to the negative 4. And so this ends up being, if I get this by itself, I end up with 4x squared equals 4.408 times 10 to the negative 5. Then if I divide by both sides by 4, I end up with x squared equals 1.102 times 10 to the negative 5. And now let's just find x. Okay, so I'll take the square root. And so that ends up being x equals 3.32 times 10 to the negative third. Now that's my x value. That doesn't really tell me what I have in the end, does it? I have to go 0.25 minus my 3.32. And so what does that give me? Well, essentially that gives me 3.32, but I could end up in my nitrogen. This technically gets me to 0.247. Okay? So again, I just plug that value in. Notice it changed very, very little because the x is such a small value. Now if I take a look at my oxygen, 0.43 minus my 3.32, that will end up giving me 0.427. And then lastly, I'm going to double my x value. 3.32 times 2 gives me a value of my nitrogen of 0.00664 molar. So that's how much I got in the end. I lost just a little bit of my reactants here, made it just a little bit weaker, and I got just a little bit, or 6.64 times 10 to the negative third molar of nitrogen monoxide. Okay, so you see the math actually isn't too bad. It's just making sure you keep track of things and learning your ice charts. Ice charts are a really slick way of learning how this works. Now, let's take a look at a 1 liter reaction container. That's cool because my concentrations are going to be given there. I don't have to figure out those things. This becomes a 0.298 molar, and I get a 0.00870 molar of the phosphorus pentachloride. All right, let's set up our ice chart though, because I see I've got at equilibrium, we're going to be trying to find out what's going on. And notice in the words here, and we have a 1 liter container, they had the following amounts. Okay, we have the PCl and we have the PCl5. Notice that when equilibrium was reached, it was found that 0.002 moles of the product had formed. Okay, so let's take a look at what's going on here. We have our ice chart, so let's keep track of the reactants and products. This is a decomposition reaction, and so I've got that. I've got my PCl3, and I've got my chlorine. Okay, so the initial concentrations, let's take a look and plug those values in. It looks like my PCl3 was a 0.298 molar. And I see that I have 0.00870 moles of my phosphorus pentachloride. So 0.00870 molar. Okay, again, it was in a 1 liter container, so I can just do that. Now they said when equilibrium was reached, we got this much had been formed as well. And so I end up with um, a, when it was reached, I should say, that's there. And that means that my equilibrium value, sorry, I just lost track of my thought there. We have the initial, we're kind of seeing those. And at the end, I end up with 0.002 because that's the change in value. Okay, now notice I'm going to work this problem backwards because it said in the end of things, when we finally hit our equilibrium, we saw 0.002 moles of chlorine had formed. So what was my change here? My change, it looks like it changed by 0.002. Now, notice that also on this side, my PCl3, so it also has changed by 0.002, which means that this guy must have lost 0.002. Okay, so what does that mean in terms of my equilibrium? Well, I'm losing 0.002, so I end up in the end getting 0.0670. This guy ends up with 0.296, and lastly, I end up with 0.002. Okay, so that's pretty, oh, I'm sorry. I'm gaining this, aren't I? And so this ends up being a 0.300. Okay, so now we're all set and we know our values. Now the question is, when all of this is done, what was my value of K? This is just a follow-up question then. Okay, and I'll just leave that in there because if I want to find my value of K, well, K of C, now that I have my equilibrium values in the end, we have PCl3, which is 0.300, and the balanced equation, there's only one of those. And so I see my chlorine was a 0.002, and there's only one of those. And on my reactant side, I have a 0.00670. Okay, and there was, again, only one of those. So my Kc value ends up being a 0.08955, or 8.96 times 10 to the negative second. Either one works in here, but again, we see we have a very small value of K. All right, so those just kind of answers a follow-up question. I figured I'd just put that in with those things. All right. Now, taking a look at a third example. Okay, I've got 4 here total for you. Nitrogen reacts with hydrogen to form ammonia. So this is one of those that I've shown you before with the initial introductory problem. So you're going to sometimes have to write and balance some equations here. Let me get this nice and neat for you. So we have nitrogen. We have nitrogen, and that's not going. There we go. All right, so we have nitrogen and hydrogen, and that's going to form ammonia, NH3. So I'm going to get 2 of those. I need 3 of these, and we end up with 1 of the nitrogens. All right, let's make ourselves an ice chart to break down what's going on. I see that it's reacting, and I'm already given my concentrations. It doesn't say anything about volume. So we must assume that we have 0.001 molar here, and we have 0.002 molar here. Okay, we want to calculate the concentrations at equilibrium if my K value is already given. 6.2 times 10 to the negative 13. This small value will tell me I'm not going to get much product. So at the beginning of it all, I start with 0. Now my change is going to be changing, but we don't know how much. And so I'm going to be losing 1 of these. Now the reason I'm doing this problem is, notice my coefficient is different, so I'm going to be losing 3 times that much, and this guy's going to be gaining 2 times that much, whatever that change ends up being. And so my equilibrium value is a 0.001 minus x. My hydrogen value is going to be a 0.002 minus 3x, and this guy is going to be gaining by 2x value. Okay? Now, notice Again, this is very, very small. So however much it's going to be gaining is going, or losing, I should say, is going to be pretty much negligent. Okay, even if it's tiny and it's 3 times, it's going to be pretty much this. So my K value is 6.2 times 10 to the negative 13. That's going to equal 2x squared over my 0.001, and it is minus x to the first, but remember, that's pretty negligent. Okay, negligible, I should say. And then I have 0.002 minus my 3x, and that's going to be cubed. But again, that's pretty negligible because my x value or my k value is so small. And so I end up in just consolidating this, I end up with 6.2 times 10 to the negative 13, that's my k value, equals 4x squared over 8x times 10 to the negative 12, or 8 times 10 to the negative 12. Okay, so if I do that, I'm going to multiply both sides by 8 to the negative 12. That's going to give me my 4x by itself. 4x squared is going to equal 4.96 times 10 to the negative 24th. And so that will give me x squared. If I divide both sides by 4, x squared is 1.24 times 10 to the negative 24. And my x value then ends up being 1.11 times 10 to the negative 12th. Okay, so that's my x value. So what is 1.00, or 0.001, I should say, minus x? Well, my n value, if I use significant figures and everything else, that ends up being still 0.001. Yes, you could subtract that off from there, but it's so small, you're going to get basically the same number. So my hydrogen, okay, now remember, this was 0.2 minus 3x. Well, 3 times 1.11 times 10 to the negative 12 is still pretty dang close to 0.002, isn't it? And so lastly, I have my ammonia. Okay, I can't cancel that out because, it's going to be basically 0, but I still have to provide a value there. That ends up being 2.22 times 10 to the negative 12th. Okay, again, not very much in there, but that then provides me with my concentrations at the end of equilibrium. Okay, last one, let's take a look. And this one is taking a look at how it might be related to pressure. Now, this is pretty simple because if I have a pressure value in here, it still is going to be a value of my equilibrium constant. We still want to find it in there, but notice that it's a function of a constant times your temperature, which is in Kelvin, and my change in the coefficients, my change in the number of those things as we go. All right, so this is pretty straightforward. If I was just going to do the math with it, and I want to see what's going to happen in this type of scenario. Okay, given this type of reaction, I want to know what my change is going to end up being, my final at equilibrium, if my pressure started out at 1.9 times 10 to the negative 3. Okay, I want to know what that value is going to be. So let's put that in, and I see that I have 1.9 times 10 to the negative 3. That's going to be equal to my equilibrium constant times my R value. So this is just a mathematical constant of 0.08206. Oops, and that's going to be times, let me clean that up, times my Kelvin. Now remember, Kelvin is degrees Celsius plus 273. They give me my temperature of 25 plus 273. That gives me 298 Kelvin. And we're going to be taking this to the nth power, okay? My change in N. So let's take a look at my reactants here. My products, I have 2 here. And on my reactant side, I have 3. So 2 minus 3, this is to the negative 1 power, okay? So if I just plug all of that in, 1.9 times 10 to the negative 3 equals K times C times 0.04089. And so my K to the C value is 4.6 times 10 to the negative 4. Okay, pretty straightforward in there. And notice it's a pretty small value of K. All right, that is the sum of the different parts that we might find within this particular chapter. I'm going to turn you loose to take a look at some other problems within the chemical worksheet.